Lecture 25, Descriptive Main Group Chemistry, Part 1, Metals and Metallurgy. Metallic elements are mostly locked up in the Earth's crust. They typically exist in ionic compounds known as minerals. Many times those minerals are mixed together with other components called ores. Ores typically contain a high concentration of a certain mineral and are what is mined to get different metallic elements. The only elements that are typically, or the only metals that are typically not part, or that you can find naturally in the Earth's crust are those noble metals. If you remember the metal activity series, these are metals that tend to be very non-reactive. These are our precious metals, such as silver, gold, and platinum, which you can find naturally existing without being combined with other elements. Here are some examples of different ores that contain high concentrations of a given mineral. Aluminum's ore is bauxite, which contains two components, aluminum hydroxide and aluminum oxygen hydroxide. The main component ore for iron is hematite, which mainly contains iron 3 oxide. The main ore for mercury is cinnabar, which contains a high concentration of mercury 2 sulfide. For lead, galena is the main ore, which contains a high concentration of lead sulfide. Finally, uranium main ore is pitchblende, which contains a high concentration of uranium 4 oxide. So, if we want to get free metals, that is, metals that are not combined with other elements, we need to do a bit of metallurgy. Metallurgical processes have three steps. The first step is a preliminary treatment, where we concentrate a certain mineral, getting it ready for the second step, which is reduction, where we reduce the metal from positive oxidation state or charge to a charge of 0, which gives you the free metal. The last step is to purify the metal through refining processes. We'll take a look at each of these different steps individually and look at some examples of how they can be done. The first step is a preliminary treatment. Remember that ores contain a high concentration of a certain mineral, but are often combined with other components that we don't usually want. Therefore, in preliminary treatment, we actually separate and concentrate different minerals from their ores. This can be done by physical processes or chemical processes. The machine on the right is an example of using a physical means to separate a mineral from its ore. The ore is pulverized or crushed up and mixed with a solution of water, liquid detergent, and light oil. This mixture is then agitated so that a foam or froth forms at the top. This froth actually contains the mineral, which is separated from the rest of the ore, which could be leftover rock and sand that settles on the bottom. The froth is then siphoned off, and the mineral is separated from it. That is an example of this physical process. Let's look at a couple of chemical processes. The first is an older process called the Bayer process, which actually is a process in which aluminum oxide is concentrated from bauxite, the major component the major ore that contains aluminum. This is a 3-step process. The first step is to take bauxite, which is a mixture of aluminum hydroxide and aluminum oxygen hydroxide, and reacting it with NaOH. This converts all of the components of bauxite into sodium aluminum hydroxide. The AlOH4 minus is a complex ion that is combined with sodium. This is done at very, very high heat. The second step is to allow that solution to cool down. When this occurs, the sodium aluminum hydroxide then decomposes into aluminum hydroxide solid and NaOH. Now all of the bauxite is converted into aluminum hydroxide solid. The last step involves taking the aluminum hydroxide, filtering and drying it, and then subjecting it to high heat. This decomposes the aluminum hydroxide into aluminum oxide and water. This step is done because oxides are typically easier to reduce than hydroxides. So therefore, we've now concentrated and converted our aluminum ore into something that is going to be very useful for the next step. Another useful process in actually preparing our ore for reduction is through roasting. In roasting, a mineral is heated in the presence of oxygen to form a metal oxide. These metal oxides, once again, are much more reactive and receptive to undergoing reduction. For example, after concentrating lead sulfide from galena, we can actually roast it to form lead oxide, which is easier to reduce than lead sulfide. In this reaction, we take lead-2 sulfide, heat it in the presence of oxygen, forming lead oxide and sulfur dioxide gas. After doing a preliminary treatment on your ores to obtain minerals with high concentrations of metals, it's now time to do reduction. This is the key step, converting a metal that has a positive charge into a free metal where the atoms have no charge and are not combined with other elements. There are two major ways to actually undergo reduction. We can do this chemically through means of a chemical reaction, or we can do this through electrolysis. We saw electrolysis in our electrochemistry unit, where you can take molten ionic compounds and reduce the metal cations into free metals through electrolysis. Let's take a look at an old familiar chemical reduction process. You might remember the most spectacular general chemistry lab in your life, which was the metallurgy lab. In the first step of the metallurgy lab, you did a chemical reduction of lead carbonate into lead metal. This was a 2-step process. You might remember that you took your lead carbonate and wrapped it in filter paper before putting it in your crucible. Upon heating, 2 things occurred. The first thing that occurred is that lead carbonate decomposed to form lead oxide and carbon dioxide gas. The lead oxide is then more susceptible to chemical reduction. The reducing agent in this case was your burnt up filter paper that served as a source of carbon. In this reaction, lead was reduced from a +2 charge to 0 charge, and carbon was actually oxidized from 0 to +4. Chemical reductions such as these are actually one of the main ways that we get iron and other metals that are in the middle of reactivity. In terms of reactivity, I should say. For more active metals, which are locked up in very stable compounds, we need to turn to electrolysis. We use aluminum a lot nowadays, and it's sort of hard to forget that when aluminum was first discovered, it was considered a precious metal because it was difficult to find as a free metal in the Earth's crust. The Washington Monument actually used to have an aluminum top because of this, because aluminum was considered to be very precious. It wasn't until the Hall-Héroult process came along, which was an easier commercial way of getting aluminum through electrolysis. To the right is an example of a Hall-Héroult cell. In this cell, we use graphite electrodes, and we take aluminum oxide, which you can obtain through the Bayer process, and melt it down and mix it with another ionic compound called cryolite. Cryolite is used because it's a very strong electrical conductor when molten. Our molten mixture undergoes electrolysis. And unlike many of the electrolysis cells that we've seen in the past, the graphite electrode is actually not very inert here. It is actually consumed by the electrolysis process. In the Hall-Héroult cell, at the anode, carbon is oxidized to carbon 4+ and CO2. These are the gas bubbles that you see coming off of each electrode. At the cathode, molten aluminum, not aluminum aqueous, sorry about that, guys. Molten aluminum is actually reduced to aluminum liquid, which congregates at the bottom of the cell and is siphoned off as the reaction is undergone. So those are two different methods of reduction. It can be done chemically through processes of chemical reduction, usually with carbon, which is very common and prevalent, or it can be done through electrolysis, especially if the metals are very reactive, such as aluminum, sodium, magnesium, things like that. The final step in our metallurgical process is refining. In this stage, your now free metal is purified using chemical or physical methods. If a metal is pretty volatile, you can actually do the physical process of distillation. However, you can use electrolysis again to refine many other metals. For example, the electrolytic cell on the right is used for purifying copper. An impure copper sample is used as the anode, and when electrolysis is undergone, the copper from the impure cathode is oxidized into copper 2+, which goes into a solution of copper sulfate and is reduced at the cathode, forming a very pure copper strip. Impurities either stay in the solution or they collect at the bottom of the anode in a little sludge. Okay, and that's the end of our lecture on metallurgy. Pretty short lecture, guys. So have a very nice weekend, and we'll continue talking about the chemistry of main group elements next week.